What's up, guys? Welcome back. I think it's episode 123 today, maybe 122. I don't know. I honestly can't remember. What did we do? We did 122 yesterday, so we're at 123 today. Pokemon 123, we got a Scyther today. A little classic one. Yeah, so let's take a look at the sound. Sorry, guys. I'm a little out of it today. Woke up today, got kind of tilted playing some chess games. I don't know. I'm just not feeling it today, so it's okay. I guess it's all part of the learning process, trying to learn how to play, so but it's alright. Gotta keep moving and move on, so let me think. Okay, so we're looking at the Pokemon. Oh, jeez, I'm kind of out of it. Sound. Oh, jeez, Scyther.
Who's that Pokemon?
Scyther!
Scyther! There's our sound. Let's take a look at our problem of the day. Yeah, I feel like you gotta take games like that, just like, I don't know, it's all part of the learning process, and I feel like people learn at, different levels and, different paces, so just feel like as long as you're being consistent, that's all you can do. So, let's take a look at this set matrix zeros. We have solved this one. I think this was definitely would have been a little while ago, December 16th. Let's take a look here. Given m times an integer matrix, if an element is 0, set its entire row and column to zeros. Alright, so I think we got to take the rows here. Cols is equal to the length of rows 0, right? Let's just print it just to make sure it looks correct. Whoops, I meant matrix, not rows. Whoops, matrix. Okay, got our rows and our cols. Okay, here, so we got, given m times our matrix, if an element is 0, set its entire row and column to zeros. So I'm trying to think how we would do this properly. If an element is 0, set its entire row column. So if this is 0, it'd be here, here. Okay. We got a 0 here, so we go here, here. So I guess I kind of feel like we're going to have to keep track of the original matrix with our actual zeros in it. Because if we make this row 0 and this column 0, right, then pretty much we're going to make the whole matrix 0, right? So we got to keep track of the original one, but then also keep track of a new matrix where we will store our answers, right? So let's call it new matrix, and we can make it matrix. Does that work? I don't know. I think that might work. I don't know. Print new matrix. Okay, yeah, that worked. Okay, so Okay, so if we go for I in range length matrix, right? For row in rows, for col in cols, if matrix row col is equal to 0, then how would we make that whole row? How do we make that whole row 0? How do we access the column? I don't really know how to do that. Actually, we can just look it up. In a 2D matrix, okay, that's an interesting way to do it. Didn't really think about that. 0. Let's do sets to 0, right? So they do 0 rows is equal to set. 0 cols is equal to set, right? And when you see that 0, we store 0 rows dot add row, 0 cols dot add col, right? Then we go for row in rows, for col and cols, if row in 0 rows, and I guess we do all col in 0 cols, then we would want to just make that matrix, sorry, it would be new matrix row col is equal to 0. Then we would return new matrix. For col and rain. Oh. What do we call it? New matrix is not defined. Let's misspell it. Whoops. There we go. Sure, there's probably a faster way to do this, I feel like. Let's see what I did in December. Okay. We did it as an n-cubed. This be n-cubed? I feel like this is an n-cubed approach. Okay. Alright. So we did the problem of the day. That's good. That's good. Good stuff. Oh, jeez. Save only 100 plus problems in 2025. That's cool, man. 100 days badge. How many days have there been in 2025 so far? Where are we at? May 21st, day 141. So we got pickleball paddles down here now. That's cool. Yeah, wow. So we've done 140 days in 2021, but I think we've done about 100. I think I stopped when I went back to Australia for winter break. I stopped at like 25 or something. So I think we've done about 100 days out of 140, which is pretty good, I think. Like, I get that badge on the profile then. Let's go, 100 days badge. How do we like equip it, dude? How do I make this one the active badge, dude? I don't want this one anymore. Man. Alright, whatever. Actually, hang on. Alright. Let's jump into some problems some more. Let's check out Leetcode's problems. I feel like maybe we should do a couple of these math geometry ones. I feel like these can be maybe important. At least I think maybe we should look at them. No, we've actually looked at, after this one, we've looked at everything. So we've pretty much done nearly all these problems. This is the last one we haven't really looked at. Rotate image, 48. Given an n times n 2D matrix representing image, rotate the image by 90 degrees clockwise. Oh, jeez. You have to rotate the image in place, which means you have to modify the input 2D matrix directly. Do not allocate another 2D matrix and do the rotation. Clockwise. Rotate an image by 90 degrees. 90 degrees, would that just be... Would that just... So pretty much 1 would go here. Yeah, okay. 3 would go here. 7. 9. So if we were to rotate this... Man. Man, guy keeps texting me. Given n times n 2D matrix representing an image, rotate the image by 90 degrees clockwise. 1, 2, 3. 15. Where's 15 here? Okay. 5. Okay, so somehow we gotta get the... Well, I feel like to rotate this properly, we gotta get the rows, right? So the rows is equal to the length of the matrix, right? And then we need to get the cols, which is equal to the length of the matrix, right? So let's print our rows. I used to hate 2D matrix problems, but now I like them, like, because they're easy to think about. There's not many ways that you can really do it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 3 and 3, right? So I'm thinking, maybe we can do the same technique as before by creating a new array. But doing it in place. Can you do this iteratively though? I don't really know. Yeah, I don't know how you would do this in place. Like generally, I have no idea. To do it, if we were to create a new matrix and do it, just for the hell of it, why don't we do this? Well, we create a new matrix, so let's do rotate image. So new matrix is equal to the length of, well, let's do 0 times matrix. How would we do this? Okay, so that's how you do it. New matrix is equal to do string comprehension. So we do 0 times n for something in range length matrix. to n is equal to length matrix. Okay. Well, I suppose calls for fill the rotated matrix. So we go for I in range. For call in range calls. We'll do the new matrix is equal to J n minus 1 minus I is equal to matrix row call. Row call. For call in range calls, right? We just want to do, well, the matrix row call is equal to new matrix row call, and then we just want to, like, I guess return our matrix, right? Call row. Okay. Well, what are we doing here? So we're going for our own calls, going new matrix. We're accessing our column as the row. What just happened? Bro. What just happened? No, wait. Rotate. N minus 1. Okay, call. N minus 1. Okay. I understand. N minus 1. N being the length of the matrix, right? So the length is 3, but really to access it needs 2. So you access it using 2, and then you do, but you minus row, so it accesses 0. So if you were to access here, it would be, well, again, it would be 3 minus 1, which is 2. And minus the row, which is 1. So it would be row 1. Okay, coal is 2. Matrix col. I'm just trying to wrap this around my head. I'm a little slow, but so we have column, right? And our column here, in this case, we want to rotate this one, right? So range calls, we do U matrix call. Col is 2. So, but wouldn't col be here as well? That's what I don't understand. I would think col would be here, because wouldn't this row be here? Because we're at 0, 2. Not the other way around. Okay. No. Let's do extra space, right? That's what I'm not understanding, because U matrix, it would be 2, 0. Col 2, but this is technically the row. Wait, I think I'm getting it wrong then. Col is currently 0, so we're looking at this value. Col is currently 0. We'd be... Oh, we're calculating backwards. That's why. Okay. So at 0, 0, when we're looking at this value, our col is obviously 0, right? Because both of them are 0. This is 0, 0. So 0, n minus 1, which is 3 minus 1, 2. 2 minus 0, which is 2. So we're pointing at 0, 2, and 0, 2 points here, right? Then we go to the next iteration where we have 0, 1, right? Again, col is 0. So then we're pointing n minus 1, 3 minus 1, which is, sorry, our length. Okay, our length is 3 still. So yeah, 3 minus 1 is 2. Minus the row, which is 0. So then our col would be 1, 0. 1, 0. Here. Yeah. That's wrong. A col would be 1. Then this would be 2 still. How am I getting this wrong? So then we go here. This should instantly be 2. We go here. We'd be at 2 here. Our col would be 2. So our row would be 2. And then it would be 2 again. Yeah. Okay, I understand. I think I'm just calculating it wrong in my head, bro. Like, I don't understand. To do it in place, though, I feel like it's tough. Let's do it in place, right? Okay. For row in range rows, col in range cols, we do matrix row col, then matrix col row is equal to matrix col row matrix row col. So I feel like here in Python we're just swapping the values. So we're swapping row col with col row and col row with row col. So if we're at 0 0 and we're looking at 0 0 col row, swapping these with each other, right? But then we come here and we're at 0 1, then we're swapping 1 0 col 1 row 1 0. Okay. Let's get rid of these prints. Okay, let's actually print this matrix. Let's print the matrix after this. I'm curious to see what it looks like. Row dot reverse. Okay, let's return our matrix. Return matrix. Take a look at Leetcode's video.
This is major. It's like the next big thing. Be the creator of the next big thing. We're the movers and shakers. We are the dreamers.
Hey everyone, welcome back, and let's write some more neat code today. We're given an n by n matrix, so this time it's a square matrix for sure, representing some image, and we want to rotate that image by 90 degrees clockwise. And we are required to do this in place, so we cannot allocate more memory. We can't just make a copy of the matrix and rotate it like that. So the challenge here is definitely doing it in place. You can see that they had a original matrix like this. What they did is they took the 1 and put it over here, so 90 degrees. Basically what they did is took this entire first row and moved it into the rightmost column, right? And so they did that by moving this over here, moving this 2 over here, moving the 3 over here. And so the problem is when you're moving this 1 over here, you have to save the 3 temporarily, right? So you have to save the 3, or once you move this 1 over here, you can take the 3, save it, and move it over here. And we know that this entire right column is going to actually be put in the bottom row. So what is actually going on is this 9 is actually being moved over here, right? That's where it ended up in the result. And then this 7 is being rotated over here. So that's where the 7 ends up. The 1 ends up over here. The 3 ends up over here. The 9 ended up over here. So these 4, let's say, have been rotated so far. So now we don't have to touch them. But you can see there's a little bit left in the outer layer. So let's just worry about the outer layer so far. We don't have to worry about the 5, but in the result, we know that the 5 actually doesn't move. You know, you rotate it. But what about this 4? Now, it's basically the same thing that we did over here, right? We are rotating this. So basically, we can think of it as being in the top left, right? The original square we were rotating was like this. Now the square we're rotating is like this. It's still technically a square, you know, if you turn your head a little bit. But this is what we're doing. We're rotating this. So this 4 is, of course, going to be moved over here to this 2. And before we get rid of the 2, we want to save it and move it over here to the 6. And so in the original, we have a 2 over here, but we know that 2 is going to be rotated, right? Because this is the rotation we're doing. And before we get rid of the 6, we want to save it in a temporary variable and move it over here, replacing the 8. But we don't want to lose the 8 yet because it needs to be rotated as well. It's going to be rotated over here to this 4. And since we rotated the 2, we know there's going to be an empty spot over here for the 4 to be placed in. And that's what you have over here, the 4. The 2 got moved over here. The 6 got moved over here. And the 8 got moved over here. So this is still a rotation. And lastly, we just have a 1 by 1. We know that, you know, it can't really, rotating it will just be the exact same. So let me show you the general algorithm to solve this problem. We're going to do this in n squared time, meaning we only have to look at each cell in the matrix once. Remember, the dimensions are n by n. And we don't need any extra memory, so the memory complexity is going to be constant. We're doing this in place in our given matrix. So I like to set some boundaries. So we know that this is our left boundary and this is our right boundary initially, because we're going to rotate the outermost layer first, right? The outermost square, and then we're going to move inward, right? We're going to do the inside of the matrix. And the top boundary I'm going to place over here because that's the top. Remember, the origin over here is 0 by 0. This position is 3 to 3. It goes like this, and as you go down, it increases. And the bottom boundary is going to be down here. So immediately we're going to start the rotation. Now, how is the rotation going to go? Well, let's start at the top left because it's the easiest, right? We know that this is the general rotation that's going to take place, right? Because we're going clockwise and then we're going to do that, right? And we know we're going to keep doing that with every element in the top row. So we did the first element in the top row, then we're going to rotate the second element in the top row. And how is that going to look? Well, it's going to be pretty similar. So since this was the second position in the top row, we're going to move it to the second position in the last column, right? So in this column, we're going to rotate this one to this position. So the second to last position in the bottom row. The main thing to notice though is that this is offset by 1. This is offset by 1 from the top. This is offset by 1 from the right. And so the position that it's moved to is also going to be offset by 1 from the bottom, which is where the last rotation took place. And then this is going to be moved over here. And so as you can see, we have one last rotation to make, right, with these 4 elements, and they actually do form a square if you tilt your head enough. This is a square rotation, a matrix rotation, but notice how, since we already rotated this one, we're actually not doing 4 rotations for the outermost layer. We're doing 4 minus 1 rotations. We're doing 3 rotations, right? So even though the outermost layer was n by n, we actually did n minus 1 rotations, right? So we did 3 rotations. And let's say after we complete the outermost layer, right? Let's say we've completely rotated that. You know, we had to rotate this part, and this part. So once we do that, then we know that we actually have an inner matrix that we have to do. So we did the outermost layer, but now we have to do the inside. How am I going to handle that? Well, it can actually just be treated as a subproblem because we know no matter what, it's going to be a square matrix. So all we really have to do is take our pointers and then shift all of them by 1. So our left pointer will be shifted here, our right pointer will be shifted here, our top pointer will be shifted here, and our bottom pointer will be shifted here. And so now the last rotation seems pretty obvious, right? So it's going to be 1 rotation. It's going to include 4 elements, and then we will have our result. Now, one last thing I want to show you, and then after that rotation has taken place, we know we can update our pointers one more time. But at this point, what we'll notice is our left pointer is over here and our right pointer is here. We know that left should always be less than right, and since these pointers have crossed each other, we know that we can stop the algorithm right. We don't really have a matrix left to rotate. One last thing I want to show you about the rotation is we know that the top left is going to be put in this position, right, the 11. So we're going to cross that out. So we're going to really replace this with a 5. But then what happens to the original 11 that was placed here? Well, what we can say is, oh, let's move the 11 to a temporary variable. And now let's put the 11 over here. So we're putting an 11 over here now. But what happened to the 16 that was over here? Well, we have to put that in a temporary variable, a 16, and then move that 16 over here. So let's replace this with a 16. But what happened with the 15 that was over here? Well, we moved that to a temporary variable. And now that temporary variable 15 is going to be placed over here. So the 15 is here, and we don't have to move the 5 to a temporary variable because look, we already put it over here. So we're needing a lot of temporary variables. I can show you a slight improvement to this, which isn't required or anything, but I think it makes writing the code easier. So we know that this 5 is going to be rotated, but let's do the rotation in reverse order. So instead of moving the 5 over here first, I'm going to take the 15, which we know is going to be placed over here, and I'm going to put the 15 over here, and I'm going to move the 5 to a temporary variable. Okay, so are we going to move the 5 over here now? Nope, that's not what we're going to do. We're going to do this in reverse order. So since the 15 has already been moved, let's take this 16 and move it over here. So now let's replace this 15 with a 16. And now we know that we need to make a rotation from 11 to here. So let's put an 11 over here. And last but not least, we know that the original 5 had to be put over here, and we stored that 5 in a temporary variable. So now let's move that 5 over here. And so we did the exact same rotation, but do you notice how we did it in reverse order, right? We went counterclockwise, and the thing the reason that was helpful is we only needed one temporary variable. which will make the code a little bit easier for us. But it's not actually required. The overall complexity is still the same. The memory and the time complexity is still the same. So now let's get into the code. So the first thing I'm going to do is set our left and right boundaries. So left is 0, right is going to be the length number of columns minus 1. But we know that the number of columns is the same as the number of rows, so we actually don't need this. And I'm going to run our rotation while left is less than right. And I'm going to go from index, so let's say we're in our top row, I'm going to iterate through the entire row except the last element. So how many rotations is that going to be? That's going to be from left to right minus 1. Or in other words, we can say from in range right minus left. So this is the number that we're going to do. So if left was 0, right was 3, we would do 3 minus 0, which is going to be 3 iterations, even though we have 4 values in our first row. So I also want to have some top and bottom pointers, and these are actually going to be the same as left and right. So top is going to be the same as left and bottom is going to be the same as right, because we do have a square matrix. It's not just a generic rectangle, it's definitely a square. And the first thing I want to do is save the top left value, right? Because the way I showed you the rotation, we only need to save one variable. So it's the top left. I'm going to get that from our matrix. So matrix of top left. And just like in the drawing, what I'm going to do is move the bottom left into the top left. So in the position of the top left, I'm going to move the bottom left into that spot. The next thing I'm going to do, just like in our drawing, I'm going to move the bottom right into the bottom left. We are doing this in reverse order, basically. Even though the rotation is clockwise, the direction we're going is counterclockwise. So the bottom right is going to be moved into the bottom left. We also want to move the top right into the bottom right. So in the bottom right position, we're going to replace it with the top right. And the last thing we have to do is move the top left into the top right. But remember, we overwrote the top left position. But good thing for us, we saved it in a temporary variable. In the top right, we're going to replace it with the top left. There's just one thing we forgot to use. So we forgot to use our I variable. So you remember how this was the first rotation that we make, right? And then we move from our top left position, we move one spot to the right. From our top right position, we move one spot down. From our bottom right position, we move one spot to the left. And from our bottom left position, we move one spot up, and then we do a rotation from here, right? And then we're not done yet. From there on, we move another position to the right, another position down, another position to the left, and another position up, and then we do a rotation from these values. So we can actually handle this pretty easily in our code. We can use this I variable to handle that for us.
You thought C++ was just C with classes?
So we can add the I value to the left index, which will shift us one position to the right. And this is also the top left position, so we're going to add I to this as well. This is the bottom left position, and we know that we can subtract I from the bottom, which will shift us up by 1. And this is that same value, so we're going to subtract an I from that as well. This is the bottom right, and to shift that to the left, we can subtract I from the right index. And this is actually this is also the bottom right, so we're going to subtract I from that as well. This is the top right, and as we continue doing rotations, we're going to move down in this column, so we're going to add I to the top index. And this is the same top right, so we're going to add an I to this index as well. So basically, as I is incremented, it's going to be handling more and more rotations. It's going to shift these cells that we want to rotate accordingly. And so this will basically perform a layer of rotation. So after we've completed an entire layer, what are we going to do? We actually need to do one last computation. We need to update our pointers, right? Because now we're going to do the submatrix. So our right pointer can be decremented by 1. Our left pointer can be incremented by 1. And that is the entire code. So it's going to
This is what I'm doing here. For +1. Man, the intuition for this is just not there. So 4 yeah, matrix row call, matrix call row. Zero zero. Transpose the matrix by swapping elements above the diagonal with their symmetric counterparts. This is a good solution as well, but man, it's a tough problem. Oh, we just did this one. Symmetric zeros. Oh, jeez. I didn't even realize we just did this one. Happy number. I guess we'll take a look at happy number. I think we've done that one. I think. Here we have. Tell me if a number n is happy. I think that's a recursive problem. Happy number is a number defined by the following process. Start with any positive integer, replace the number by the sum of its squares and its digits. So we start with number 19. Replace the number by the sum. Those numbers are happy. If it's an easy problem, it's probably def recursion passing our num. If num is equal to 1, we just return, right? We can just return true, right? Let's do recursion. Pass in the string and num. Line range length num. Into I times why do we have a 4 here? If numbers equal to 2. Then we would We would need like some sort of dictionary or something, right? Where we see the number, we return true. We do like if I guess we're making this into a DP problem. Man, probably not gonna work, but if DP I guess we can just, if it is in there, we can return false, because then we know we're looping endlessly, right? For I in range length num 10 plus times I. DP num is equal to temp. Well, temp is equal to 0. Just return false. My soul survivor. I'm a soul survivor. Oh, yeah, I guess we could do a scene instead of a DP. That probably makes it easier. Scene is equal to set. Right. If num in scene, we would just return false. We would add it. Scene.add num. For digit and digit. Recursion. Temp. Main object is not iterable. Why? Passing as a string, shouldn't it be iterable? Oh shit, that's why. Not wrapping it, casting it into a string. No, we're not returning anything. Turn. How did we do it before? We did the same thing. Let's check out +1. I think I've done this one too. I'm not sure though. +1. Oh, it's an easy now? Oh, it is an easy. The larger, I'm so confused. Like, oh, okay. So we're incrementing it by 1, right? So I guess. I don't know if this is cheating, man, but you could just like, you put it int digits, digit plus or equal to 1, return list digit. I'm confused what this means. Int argument must be a string. Digit is equal to 0. We do for I in digits, digit plus or equal to I. Let's print digit. Can't concatenate. How do you add a string? How to add something to string Python. I can't remember, dude. Object is not iterable. Return list. Bro, what is going on here, dude? Digival. I'm trying so many ways for this to return properly. It's like insane. For I in digit in string digit val res.append I, and we return res. Jeez, man, this has been literally such a grind. Like, oh my gosh, dude. String digit val. Res.append I. So res.append int I. Cast into an int here. Oh geez, finally, bro. Oh my gosh. Man, that took way longer than I needed to. Python 3, 100% beat. I guess this is kind of like the bullshit way to do it, but okay, I think I understand. So we go for I in range length digits. How do we loop? We go length digits. -1, -1, -1. So that loops in reverse, right? So if we see if digits I is equal to 9, we make digits I equal to 0, and then we move to the next number. Else we would just increment it by 1. Digits I plus or equal to 1, and we instantly return digits, right? I instantly just return digits. If we get all the way through and they're all I's, then we would return Alright, so I guess if we get through all this, we can do, well, we can do digits.insert 1. Return digits. It's not insert. It must expect. What does it expect? Oh, we insert add 0, but we add 1. What is wrong here? We get to the last digit. Maybe we want to get rid of this -1. Well, no, actually, this is right. Wait, hang on. $99 goes to 100. How is this incorrect? Like, how is that solution incorrect? Oh, incrementing it in the loop, that's why. Okay. Do power xn. I actually don't know how to implement this. Like,
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve power of x to the power of n, or however you want to, say this title. And before we solve this, I just want to mention, so there's a ton of dislikes on this, but to be honest, I do feel that this is a pretty fair question. I think this is actually one of those rare medium problems that you can solve even if you haven't seen the problem before. You can mostly solve this problem. It's a little bit more tricky, I guess, if you want to, x to the power of n, well, we could have 2 to the power of 10, or we could have 2 to the power of negative 10, because actually in this case, n can be negative, even x can be negative, and actually x can even be a decimal, but that doesn't really change the problem actually. Like, 0.5 to the power of 10, it doesn't really change the problem because the math works out the same. The power itself can't be a decimal, right? We can't have 10.5. That would make this problem a little bit more difficult, but we actually don't have to deal with that case. So I do feel that this problem is mostly doable. It definitely does need a little bit of math background. So if you don't like math, yeah, you might not like this problem. But let's just refresh ourselves. So let's take a look at this first example, 2 to the power of 10, right? So what exactly does that mean again? Do you remember from your high school, middle school, college math or whatever? Well, 2 to the power of 10 is just basically a short way of writing 2 times 2 times 2, all the way 10 times basically, right? We'll multiply 2 10 times. So when you think about it, this problem sounds pretty dang easy, right? We could apply the same logic to the second example, 2.1 times 2.1 times 2.1, right? 3 times. Okay, but what about negative exponents? You might not remember from your math class, but negative exponent basically means, the same thing. So in this case, 2 to the power of negative 2 is still 2 times 2, right? 2 times, you still do it the same number of times. It's negative 2, so we'll do it 2 times. Only difference is you actually take this number and then put it in the denominator, and you take 1 divided by that number, right? So that's literally just it. Negative exponents are literally just taking that big number that we take, putting it in the denominator, 1 divided by whatever that number we calculate. So now that you know the math behind this problem, it's pretty easy to solve this problem in linear time, right? Can you see why? Because we can just do a while loop, a for loop, whatever you want to do, n times, right? So time complexity is going to be n. We just take x, multiply it n times. Now,
while n is greater than 0. Times x. Oh my gosh, we're not even decrementing, dude. Oh my god. N minus or equal to 1. Can we do temp is equal to x? Temp is equal to temp times temp. I'll put inf. Why do we get an inf output here? Oh, okay. These times are equal to temp. Okay. Literally, my thinking is just to times it, get the number, and then we check if it's negative or positive. If x is negative or positive, right? Sorry, if n is negative or positive, right? If it's negative, then we just put it over 1. If not, we just return it. Like, so I don't know. If n is greater than 0, we return temp. Else, we do 1 over temp 2 is equal to 1 over temp. And we would return temp 2.
Well, the problem is, and I'm guessing maybe this is why this problem got so many dislikes, I don't think this actually passes the test cases. Why doesn't it? Because there's a better solution. It's not a common sense solution, but it is something that you can logically figure out. So if we're taking a number x or 2, whatever you want to call it, multiplying it out 10 times, is there a shorter way to do that? Is there a, I don't want to, ruin the problem. So if you want to try to figure it out on your own, go ahead, but I'm going to mention the keyword right now. Is there a divide and conquer way that we could solve this problem? So here we have 2 times 2 written out, I think 10 times, right? So is there any repeated work you're noticing? Well, when the way math works out, multiplication, isn't it true that we don't have to do this 10 times. We could just do it 5 times, right? 5 times, half of it, right? Just do half the work. And then, once we calculate this number, which
I forgot to make this and turn that into negative.
in reality is 2 to the power of 5, can't we just then say, okay, we have that number, 2 to the power of 5, and then just multiply it by itself? In that case, we're eliminating.
Okay, so if n is equal to 0, right, we return 1. If n is less than 0, if n is less than 0, flag is equal to true. N is equal to the absolute of n, right? Because it's negative or positive. Then we loop through in range, length n. Result times are equal to x. If return 1 over x if flag is equal to true, else result. N. Cannot access local variable result. Flag is equal to false. Why are we getting 0.5? meant to be one over result. It's not going to pass. Really, dude? A recursive problem for this? Jeez. Yeah, man, I don't really like that problem, to be honest. Oh, you're going probably a little while now, dude. I'm getting kind of sick. Let's check out one more. Why not? Multiply strings. Got a 42% acceptance rate. Given two non-negative integers, num1, num2 represented as strings, return the product, num1, num2 also represented as a string. One, two, three. Okay, bro. Like, you must not use any built-in bit integer library or convert the inputs to an integer directly. Shit, man. How would you do that without... Yeah, I was thinking the same thing. It's a joke. How would I do this? 1, 2, 3 times by 4, 5, 6. I mean, do I think this is a stupid question? Yes. Okay, first we probably need a base case, right? I guess if nums1 is equal to 0 and nums2, sorry, I guess it'd be or nums2 num2 is equal to 0, right? Because anything times 0 is 0, right? So we can instantly just return 0. Return 0, right? Then I think we would loop through for I in range length of, man, I guess they could be different, so I don't know. I know we loop in reverse, right? So we take the numbers, right? You know, nums1i, right? You know, or whatever. Like, we multiply them, carry the 0, and do something like this. But I.
Fernandez cannot marry a Fernandez. Stop!
Hey everyone, welcome back, and let's write some more neat code today. So today, and
Man, what a solution, dude. Like, And that is an insane solution, dude. Like,
And then add.
also, I really don't feel like doing this problem today. I'll really think about this, watching this video, and really studying it thoroughly. I think I need to go take a break. I think I need to walk outside. I haven't really been outside in a couple days, so it sounds so sad, but yeah, I think I'm gonna take a break. I know today probably wasn't as fun problems to do, and obviously they weren't, but you know, I feel like it is kind of important to do, you know, a little bit of these problems, because I feel like, you know, they can help a little bit, you know, just taking a look at them. But yeah, they were definitely very boring problems. Probably my least favorite ones doing the math and geometry ones is like, I feel like there's I don't know. But yeah, I probably could solve this, watch Leetcode's videos, solve it, learn how to do it, learn the intuition, and I probably will eventually. I feel like eventually we'll definitely come back to this problem, but for now, I think I'm going to leave it. I just, you know, I know I'm going to spend probably an hour trying to figure this out and solving it and understanding it line by line by line, so we've already been gone for nearly 2 hours now, so I was only planning on making a shorter video today, so but I do appreciate you guys watching if you do. So I'm thinking about streaming maybe some of this, but I don't know. We'll see. I've just been thinking about it the past month or two to stream it and then just upload the raw footage on YouTube, but I don't know. We'll see. So but yeah, appreciate you guys watching, and I'll see you tomorrow.